Oh, yeah.
Thank you so much for doing
Oh,
this.
I love this. This is one of
Okay, you ready? Okay, ladies and gentlemen. I'm Judah Levine. I'm a faculty member in the physics department. I'd like to first of all thank you all for coming. It's a real pleasure to see people coming interested in science. We typically try to have one of these Saturday afternoon lectures every month. We're a little slow getting started this term. We tried to do it in the fall term and didn't quite get ourselves together in time. But the plan is to have a talk more or less every month. If you're from a high school, we invite you to sign the form in the back outside in the lobby so we know where you come from. If you'd like to get on our mailing list, you can sign up there as well. And if you have questions for Paul, you should ask them or ask them later. In general, having taught in this room, I can tell you that the acoustics in the back are kind of awkward. And if you ask a question from the back of the room, it's a little difficult to hear it in the front of the room. So you may have to shout it out or do something. Our speaker today is Professor Paul Beale. He's been a professor in the department for, I don't know, 25 years or something.
39.
What's that?
39.
Oh, sorry. I apologize. 39. 39. Okay. And he's a theoretician. He works in statistical mechanics. But he's going to talk to us today about the Big Bang. And so there it is. Paul.
Thank you. Thank you all for coming. So I've met a few folks who listened to me on Ross Kaminsky's show on KOA. So thank you especially for coming. I've enjoyed those 5 and 10 minutes science sessions on Saturdays about once a month on Ross's show. So today we're going to talk about the Big Bang. So the Big Bang is what we are. The universe was created in the Big Bang. So it's the ultimate origin story for humanity and all of the universe. So what we're going to try to cover today is where did the universe come from? How do we know that it actually was created rather suddenly about 14 billion years ago? What is it made of? And where is it going? So we are part of that story. So this is the universe before about 1920. So this is a photograph of the Milky Way. So before 1920, that was what scientists thought was the entire universe, was the Milky Way. Milky Way is about 100 billion stars spread across a rather large region of space. And all the astronomers up to that time, everything they'd ever looked at was part of the Milky Way. And that began to change by virtue of theoretical advances and observational advances in astronomy. So what you can see here are the nearby stars, and that glowing white region are billions and billions of stars, none of which you can image with your eye. But large telescopes can see deeper and deeper into the Milky Way. So this is a composite image of, from astronomers of what the Milky Way looks like from the Earth. So what we are we're in this disk of stars, and we're very far from the center of the Milky Way. And much of the center of the Milky Way is actually obscured by dust. And dead center at the center of the Milky Way is an enormous black hole. And the next Gamow lecture, which will be next spring by Andrea Ghez, is a person who studies that black hole at the center of the center of the galaxy, called Sagittarius A star. And her work was instrumental in identifying that as a black hole. Okay, so this is what the Milky Way looks like if we could look at it from above. So the sun is out here rather far from the center of the galaxy, but the galaxy extends even much farther out than that. And that little red circle, every star that you can see with your eyes is in that tiny little circle of the Milky Way. So the Milky Way is much, much, much bigger than what we see with our eyes. And looking at it edge on, you just see this cloud of white. And that's been known for millennia to human observers of the sky. So it's about 180,000 light years across, has about 100 billion stars in it. There's probably 100 million black holes hiding in the various parts of the Milky Way, including the supermassive black hole at the center, deep inside that region right there. And it has a mass of about 4 million solar masses. So over the course of its evolution, it's just absorbed star after star after star, have fallen into that black hole. Best we can tell, nearly every sizable galaxy contains a supermassive black hole. Now, the sun orbits the center of the galaxy due to gravity, and it takes about 250 million years to orbit the entire galaxy. Oh, so if you have questions, you can raise your hand, but if you speak up a little, I'll be able to identify you and answer questions as we go along. So I'm a teacher in this room a lot, so answering student questions is the best way to actually make sure everyone is on the same page of what we're talking about. Yeah, is that a question? So this is, again, with the ones we know about in the region close to the Earth, extrapolating that to the whole galaxy tells us we can estimate it to be about 100 million across the galaxy. Many stars form a black hole in the end stages of their life, and so it's not the only way that they can end, but it's one of the common ways a star can end its life. Yes, sir? I am not an astronomer, so the question is, why is there so much structure in the Milky Way? I'm not an astronomer, so I'm going to defer that to some expert sometime to answer that question. But many of the spiral galaxies, this is called a spiral galaxy, have this structure. And occasionally two galaxies will run into each other and create an even more complex structure. In fact, the Milky Way and the Andromeda galaxy will be running into each other in a few billion years. So exactly that process is going to happen, and this stirring of the stars creates this very complex structure. Yep. Oh, yeah, here we go. I wish I knew. I grabbed this one off the internet. So they were trying to talk about particular types of stars and where they are. And so not quite sure what those were referring to. I just needed a nice from above picture of the Milky Way. Okay, so one of the stories of the universe came out of the mind of Albert Einstein. So in In the period 1905 to 1919, he created the theory of relativity. First, the special theory of relativity, the most famous equation being this one, E equals mc squared. The energy of an object is equal to its mass times the square of the speed of light. And since the speed of light is a very large number, Judah will appreciate I have the exact value here. So the scientists at NIST and other scientists around the world have decided that that is the exact value of the speed of light. And then everything refers to, for example, the distance, what we call the meter, refers to how far a light beam travels in 1 over that fraction of a second. When we include momentum of particles, the energy becomes not just mc squared, but includes this term called, proportional to the momentum, P. And that's an important feature of particles. And there are particles without mass called photons. We'll talk about them later. And they have energy even though they have no mass. And they have an energy that's equal to, see if that term is 0, the energy is just the speed of light times their momentum. And that's an important feature of the discussion we'll do later. And then in the 1910s, he developed what is known the general theory of relativity. And it's encoded in this equation. G mu nu refers to the curvature of space and time. And T mu nu refers to the energy density contained in any region of space, energy per unit volume. And the more energy there is in a region of space, that could come about from mass or from other kinds of energy, makes this curvature. So the more energy is localized in one space, the more curvature there is. And if there's enough energy in one location, the curvature is so much it creates a black hole that light cannot even escape from the black hole. So here's sort of what a pictorial description of what mass does to space and time. So as a star moves through space and time, it actually warps the space around it. So it sort of contracts the space and creates a curved space. And the motion, in fact, the force of gravity comes about because of that curvature of space. Okay. So it was presumed at the time, since the universe was this thing we could see and it didn't seem to be changing very rapidly, that the universe was constant in time. Yeah, there's a question right here.
So that video that you were showing of the space-time being curved through the star moving, what makes the space-time like grid relax back to its original?
Oh, okay, so it's only, okay, the question is the curvature only is present if there's mass present in some localized region. So if the star is there, then there's a curvature, and if the star is not there, then it's what we'd call flat. That the lines of space and time are smooth and flat. What we would call Euclidean geometry. If you draw a triangle, the angles add up to 180 degrees. That's not true around a star. So the assumption was the universe was, as a whole, static, and this was Einstein's view. It was everyone's view at the time. And Einstein wrote down in his equation, and he said, not just applies to the sun and the moon and the earth and the planets and the nearby stars, it applies to the whole universe. And this person who was a priest, Belgian priest named Georges Lemaitre, studied Einstein's equations as a hobby and was able to show that that equation did not allow a static solution. There's no way you could write that equation down, start the universe off, and it would stay put. It would always either contract or expand if you start with that equation. And he and Einstein ended up in several public debates about that. And Einstein couldn't find anything wrong with it, with Lemaitre's mathematics. But he said, you just don't understand the physics. Well, turns out he understood both better than Einstein did at that time. But Einstein finally figured out, it's like, oh yeah, okay, I think I see what you're saying. Let's see if we can fix my equation to allow for a static solution. So in addition to the curvature term and the energy term, he added this term called the cosmological term. And it's allowed by the symmetry of his equations. And so from a theoretical physics perspective, it's like, yeah, if it's allowed, why not? So he put it in. And G mu nu is describes the flat space-time. And this constant lambda creates a uniform outward pressure. So gravity tries to pull things together, and this term, cosmological constant, tries to push things apart. And if you adjust things just right, you can make the universe static by virtue of putting the right size cosmological constant in. So Einstein was very proud of himself for doing that. And then about a year later, the astronomers took over and showed him that this was not the way to think about the universe at the time. So this is a picture of the Andromeda Galaxy. It's the largest large galaxy near our Milky Way. It's a little bigger than the Milky Way, not a lot. Similar number of stars. And it was just a fuzzy thing to most telescopes, because as telescopes got better and better in the earliest 20th century, Edwin Hubble and other astronomers began to notice that if you focus in on the Andromeda Galaxy, every smudge in that thing is not just some sort of gaseous smudge, it's actually a star. So there's 100 billion stars in that thing if you focus in, and that's a photograph of Andromeda, I believe, by Hubble. Every dot in that picture is a star in the Andromeda Galaxy. So Hubble was able to measure the distance to that galaxy. And here's a pictorial description. Here's Andromeda. It's about 220,000 light years across. Our Milky Way is a little smaller, but this distance is 2.5 million light years. So it's way outside the Milky Way. So that was the first indication the Milky Way was not everything. In fact, it was only a dot in the universe. That Milky Way, as big as it was, is just where we happen to be, and there's a lot more of those things all over the universe. So the question is, how could he measure such a huge distance? So let's talk about a little physics. He used an idea called a standard candle. And so if you take a light bulb and you measure how bright it is to your eye, or with a telescope from a good distance away, if you know exactly how much power it puts out, like 100-watt light bulb puts out 100 watts of energy, 100 joules per second. If you measure it from some distance away, it will have a certain brightness, a certain watts per square meter will reach your eye. Whereas if you go twice as far, the intensity will be 1/4 as big. And it's the scaling of the intensity with distance allowed him to measure the distance to the Andromeda Galaxy. With nearby stars, you can actually measure how far they are away by a method called parallax. As the Earth goes around its orbit, those stars will move ever so slightly in our field of view, and we can measure their distances. So we have a good physical measurement of how far away they are. And there are some stars that are called Cepheid variable stars that, depending on they have a very peculiar brightness versus time behavior, and if you could measure the distance to those, there was a pattern that Hubble developed that said, oh, I know exactly how bright that star is based on this pattern of the rising and falling of the luminosity of the star. So what he did is he pointed his telescope at Andromeda, and he saw Cepheid variable stars in Andromeda. He saw them, they had this exact same pattern, and he knew how bright they were, therefore he could infer what the distance was. And that's where he came up with this 2.5 million light years distance for the Andromeda Galaxy. So he's using a very simple physical principle. Best science is based on simple ideas that everyone can understand, and then you use sophisticated ways of measuring those simple ideas. Now, another way to measure distances, and it becomes very important in the story, is supernovae generate a brightness that is a well-defined known brightness, or a certain kind of supernova called a type 1a supernova produces almost exactly the same amount of brightness as any other one. And so if you can spot one of those, then you can figure out how far away it is. These happen in our galaxy about once every few hundred years. And there's been one in our lifetime, where there was one in 1987. And this is a picture of a supernova in a relatively close by galaxy, but you can see it for a few days outshines the entire galaxy. So if you can spot a supernova, and if you sort of search the sky every night and look at every galaxy that you can put your telescope on and look for these bright events, then you can identify exactly how far away that object is, because that is a standard candle. Questions? Okay, another thing that Hubble did after he discovered that Andromeda was not part of our galaxy, he started measuring the other galaxies that were surrounding our galaxy. And he noticed that some of them are moving toward us and some are moving away. And he measured the speed at which they move away or toward us using what's known as the Doppler effect. So if you're standing in front of a police car that's moving toward you, you hear a higher frequency. And if you're behind that police car, you'll hear a lower frequency. So what you'll hear is woo, 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 as it goes by. And that's the sound you love to hear, because that means cops going after somebody else, right? Well, the same thing happens with light. Blue light has a smaller wavelength, a higher frequency than red light. And so if an object is emitting light and you're measuring it from this direction, what you would see is a slight blue shift, that you would see the light is getting to you at a slightly higher frequency than the way it was emitted. And the person who's standing behind the moving object would see a slight red shift. And we have very precise ways of measuring that, because atoms emit very precise frequencies and wavelengths. So when you heat up sodium in a flame, it gives off a very specific yellow light. And that yellow light has a very well-defined wavelength and frequency. But if that star is moving toward you and you can spot the sodium spectrum, then you can determine exactly how fast it's moving toward or away from you. Question? Is that how we discovered that the universe is expanding? Ooh, I'm getting there. So this is how we know the universe is expanding, and I think you've anticipated my next figure. So Hubble measured the distance to nearby galaxies, and he measured the speed at which they were moving. And what he discovered is the ones that were further away tended to all be moving away from us, and the farther they were away, the faster they were moving. This is what's known as the Hubble diagram. So this is using supernova events, and this comes from the Hubble Space Telescope data. So the velocity of moving away measured in kilometers per second. So they're moving away at quite a clip. For 40,000 kilometers per second is a very big velocity, and that's how fast the faraway galaxies are moving away from us. And the distance to them you can measure using these standard candles of supernova, and the Hubble is able to measure out to about 2 billion light years. Question? Why is it easier to observe it with sound or light? Okay, so in sound, the speed of sound is only 340 meters per second. So a police car moving at a normal speed will produce a noticeable shift, whereas the speed of light is 300,000 kilometers per second. So to your eye, you would have to see something moving very rapidly to measure it, but scientists can measure that using a spectrometer to very high precision. Okay, so your eye can't see it, but a spectrometer can. Very good question. Okay, so this is data that goes out. They're using a distance measure called a megaparsec. Parsec goes back to that idea of as nearby stars move in the field of view by a certain amount, and that's the standard measurement distance that astronomers use. But converting to light years, that's about 2 billion light years. Okay, you'll notice that data falls on a nearly perfect straight line. Hubble's original data would fit down in that red box there, and it was already a pretty straight line in Hubble's Hubble's original data set. Okay, so this is a deep field image from the Hubble Space Telescope. So they aimed the telescope at a spot that appeared to have no stars in it, and as best they could tell, almost no galaxies in it. But the Hubble Space Telescope was so precise and so sensitive to measuring objects that every object in that figure is a galaxy. So this thing is, I don't know, probably the size of a grain of sand at the end of your hand, looking out into space. This is a very tiny region of space that Hubble focused on for days and days and days of collecting data. And this became one of the most famous images in astronomy. Every object in there is a galaxy, with the possible exception of that one thing right there. So there are hundreds of billions of galaxies, each of which contain hundreds of billions of stars. And the distances here range out to about 13 billion light years. And as I'll come in a moment, we'll see that that was very close to the beginning of the universe, is when the light was emitted from some of these galaxies. So you can actually see the extreme redshift in this figure. So focusing in on these numbered values here and blowing them up, these are each galaxies, and what you're seeing is a very, very red-shifted galaxy. The light that was emitted was mostly in the visible and ultraviolet and near infrared, but by the time it gets to us, having traveled across the universe, they're moving away from us from this redshift. What you see is just these very red dots. So you can see how far away, how fast they're going away from us by virtue of their sheer color. But we wouldn't rely just on that. We would actually look for the spectral lines from each of those galaxies to make a precise measurement of that velocity. Now, astronomers also use, here's another picture from Hubble, they use Einstein's gravitational lensing to even see farther away. So occasionally there'll be between us and some distant star a big set of galaxies, and space-time is curved around those galaxies, and it creates a lens. And so that object right there is the farthest star that's ever been imaged, and it's estimated to be about 12.9 billion light years away when it emitted its light. Okay, so by luck, that particular star was in a perfect focus for the Hubble Space Telescope. Now, the James Webb Telescope is designed to look in this exact region of space far from us, where the redshift is huge, and it does that by focusing all of its using light in the infrared part of the spectrum, the part of the spectrum that's far longer in wavelength than the light that we can see. And because of that, then it can just gather a lot more data about those very, very distant galaxies and stars. So some of these were formed only a few hundred million years after the Big Bang. Okay, so how is it possible that the universe, everything's moving away from us? That seems bizarre. Okay, so here's a little picture. So here is the Milky Way galaxy, and we look at the nearby galaxies and even the ones farther away. They're all moving away from us, and the ones that are farther away are moving faster away from us. So it looks like we're in a peculiar space somehow at the center of whatever this is. But that's not the case. Let's look and see what people in this galaxy see. They see exactly the same thing. They see the nearby galaxies moving away and the ones that are farther away moving away faster. So if this happens in this particular way, the entire universe is expanding, and it's just since it's expanding, this fabric of space-time is expanding. What we see is the farther away galaxies are moving faster away from us. This is called the cosmological redshift. So we don't think of this, astronomers don't think of it as they're physically moving away from us. They're sort of trapped in space-time, and space-time is stretching, and the galaxies move with the stretching of the space and time. So I have one demo for this talk. Here's a balloon. I've drawn little galaxies on it, and So they are close together on the balloon, but if I blow the balloon up, the fabric of space-time has expanded. So the more the fabric has stretched, the farther apart the galaxies have moved. And so that's what's happening with the universe. The fabric of space-time carries the galaxies along with it. So what we're seeing is not the physical motion through space-time, but rather the stretching of space-time itself. There we go. That's a physics class. You got to have one of those. Rocket propulsion. Questions? Okay. Here's one. Yes. Oh, two back here. Shoot.
If time is compared to a balloon, then technically you'll run into the complication that eventually space-time will pop like a balloon.
Ooh, very.
And yes, I have in fact knew this since second grade.
Okay, we'll talk about that a little later. The fabric of space-time is stretching, and as we'll talk about, it's stretching, not slowing down, is in fact speeding up. Question?
I might have mentioned this already. To be honest, I might have zoned out. So is the reason the farther galaxies are moving way faster just because all of space-time is expanding and there's more space-time between us?
That's a very good analogy. So it's the fact that there's more space-time between us, and so since it's all stretching at a sort of a steady rate, they're moving apart faster. What we see is a bigger redshift. In fact, the way we think about the redshift is not that it's what we call the Doppler shift. It's more that the light was emitted and space was stretched as the light was moving, so its wavelength was stretched along with the stretching of space and time. Yes, sir.
From a gravitational standpoint, from the Big Bang, assuming there's some
Mm-hmm.
was or wasn't, that then the energy moves it out, right? And how could there be more energy to move this space-time out without it eventually beginning to?
Very good question. So in Einstein's equations, there's mass and energy contained in space and time, and so as it's moving out, gravity is an attractive force. That's going to slow down the expansion of space and time. And up until 1995, that's what everyone assumed was happening, that the universe was expanding. It was created at a specific moment in the past, but its expansion was slowing down because of gravity. But it was slowing down at a very precise exact rate that said that the overall universe has this property that Einstein would say was flat. The amount of energy of its expanding was exactly compensated by how far apart the galaxies were. So we'll come back to that question. So the universe is expanding, but it's not just expanding, it's accelerating as it expands. Okay, so this exact process is going on is Einstein would say that space-time is flat. It has this very precise connection between the gravitational pull and the velocity of escape. So it's basically, it's like saying that every galaxy is at the escape velocity from every other galaxy. Another thing to be pointing out, we'll come back to where this number comes from in a moment, but we can't see all of the universe. We can only see the portion of the universe that light has had a chance to be emitted and reach us. So we can't see anything more than 13.77 billion years. Best we can tell, the universe is much, 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 much bigger than that. We're only seeing a small piece of the full universe, just as in the Milky Way, we're only seeing with our eyes a very small piece of the Milky Way. So the universe is way bigger than what we can currently see. And as time goes on, we see a little bit more and more of it, but the universe keeps expanding as it's doing that. Okay. So let's try to explain what's going on here. So Lamont came to the rescue again. So Einstein's original equation allows for an expanding universe that began a finite time in the past, and he coined the term a day without a yesterday. Now that's a poetic description of the Big Bang. So he used just Einstein's equations about energy and curvature are connected with one another. And if it was exploded outward, we'll talk a little bit more about what that means, then it would expand in a very precise way. And that was a possible solution of Einstein's equations. Now, another character in the process at the same time was Alexander Friedmann. He was actually George Gamoff's initial PhD thesis advisor. Gamoff will appear in the story in a few slides. So the age of the universe is the inverse of the slope of that line. Okay, that Hubble's parameter is the slope of that line. And 1 over that has units of time, and it's precisely the age of the universe. So it's the time since the universe began that slope of that line represents. So you can measure that. That's been measured, and that's the figure. You just take the slope of that line, take the inverse of it, and the number comes out to be the current age of the universe, 13.77 billion years. Now, the astronomers are now arguing about that decimal place, basically right there. Okay, so in Hubble's time, the number was somewhere between 5 and 20, so he had a large uncertainty on it. The more and better we measure, the more and more precise this number becomes. That's a good test of a theory, is that you start arguing about higher and higher and higher decimal places in the measured properties from the theory. Question?
Isn't there a discrepancy between the JWST measured and the
Right, so the question here, is there a discrepancy between what this number is? There's several ways of measuring it. One is measuring from the cosmic microwave background, which we'll come to, and one is measuring it from that plot. And they are disagreeing sort of in, that decimal place or so, So it's a little further in because it's a very different measurement. And astronomers are beginning to argue about that and seeing which one's the better measurement and are they consistent with each other.
Because I've also heard that the error is so low to where they don't have any overlap anymore.
And that's where science really gets interesting. The overlap is beginning to be a problem for the theorists. And so that's when science gets interesting, is like, ooh, our theory needs something better. We need to take it to the next level. So many of the great revolutions in science have happened with just those kinds of discrepancies. Okay. So back to Einstein again. He says, oh, darn, I didn't need to put that thing here in the first place. Don't need that. He, in fact, told his friend George Gamow that he considered it to have been his biggest blunder in science. But as we'll see, it may have actually turned out to be his greatest success. That cosmological constant actually corresponds to most of the energy density of the universe is hiding in that number right there. Okay, so this takes us to the late 1940s. George Gamow, whom the tower in this building is named, he was a professor here from 1956 until 1968, and he published the first paper on what what's now called the Big Bang Theory with his student Ralph Alpher. And here's the key idea. And again, a simple physics idea is what's really valuable to be able to take a calculation forward and believe your result. So the universe is expanding, so the matter in the universe is getting farther and farther apart. So applying the laws of physics in the distant past, everything we now see in the universe would have been compressed into a much smaller space. So everything we now see must have been in a much smaller space, so much more compressed. And when you compress a gas, its temperature goes up. It's a fundamental idea about thermodynamics. So it's the second law of first and second law of thermodynamics is temperature is going to go up if the gas is compressed. And so the idea was, let's take the laws of physics and run them backwards. Turns out almost all the laws of physics precisely run backwards exactly the way they run forwards. Physicists are perfectly happy setting time equal to minus time and running the equations backwards. And that's basically what Gamow and his student did. So not only was the universe much denser, it must have been much hotter as well. Okay, so here's a sense of that. So here's a distribution of nearby galaxies, a little pictorial representation. It's about 1 per trillion cubic light years. That's now. Well, the universe, when it was smaller, when it was 10 billion years old, the distances between the galaxies were 1/10 as big. And so that meant the density would have gone up by a factor of 1,000. So the galaxies were 1,000 times more dense. And if you go back in time a little further and look at individual molecules of gas, here is extragalactic space has about 1 atom per cubic meter. Round numbers, that's a pretty good number to determine how many atoms there are in the universe. And they're very cold. And if we run time backwards, they get closer together. So at this 10 billion years ago, they would have had 1/10 as large a distance between them, or about 1,000 times denser. And the temperature would have not been a current temperature of 3 degrees, but 30 degrees would have been hotter. Measuring temperature in what's called Kelvin scale, that's relative to absolute zero. Well, about 380,000 years after the Big Bang, that is this moment in the past when the universe was created, the density would have been about 1 billion atoms per cubic meter, and the temperature would have been about 3,000 degrees Kelvin. So at that point in time, the universe would have been really simple. And this is Gamov's idea. It's like, oh, the universe is complicated now. Let's look at it when it was simple in the distant past. So what's that temperature? That's about the temperature you would see in a lightning strike. And for the same reason, the temperature is such that it takes the electrons off of the neutral atoms, creates a plasma, and the plasma gives off light, and that light has a characteristic color depending on its temperature. And so the universe would have been a big glowing plasma at that point in its time. And we have a really good idea how to study the thermodynamics of that material. That's a very well understood physics laboratory material. Okay, so here's a sense of that. This is a picture of, that's a piece of tungsten that's at a temperature of 3,000 degrees Kelvin. And this is the color that would have been everywhere in the universe at that time. And just to give you a sense of that, what's that color? This white patch here was not, is not a white patch, but it was actually grabbed from the image. Okay, so what we're seeing there is the glowing that's given off by something that has a temperature of 3,000 degrees. Anything that has that temperature will glow exactly like this. This is called the black body radiation. Okay, here's a demo. So this is these are the visible light that you can see with your eye. If an object has a temperature about equal to an incandescent light bulb, about 3,000 degrees Kelvin, it gives off wavelengths that are mostly in the infrared. This is the longer wavelength portion of the spectrum. And less of the reds and blues. So when things get hot, like your toaster oven, what you see is a reddish color as the toaster oven carries the temperature. So the temperature, the color of the wires inside your toaster oven are telling you what the temperature of the oven is. If we raise the temperature up a little bit, that's the temperature of the sun. Then what you see is the sun's emitting about equal amounts of red, Roy G. Bibb, red, orange, yellow, green, blue, indigo, and violet. It's one of the few acronyms that I've tried to commit to memory. Physics is not, the best thing in physics is not memorizing things. But this is one I could never quite remember the order of the colors. But so it's red and orange on this end, blue and indigo and violet on the other end. As you go higher and higher temperature, like the brightest star in the sky is Sirius A. Its temperature peaks out in the ultraviolet portion of the spectrum. So if you look at Sirius, that's the eye of the dog that follows Orion across the sky. It has a bluish color because it tends to be emitting more blues than reds. 2. Okay, so here's where Gamov's genius comes in. Don't stop there. Let's take this to the next level. So the universe, when it was 300,000 years old, would have been glowing at 3,000 degrees Kelvin. Why not run the clock back further and further and closer to the beginning? So the laws of physics, as he understood them already in 1948, he could run the clock back till about a hundredth of a second after the Big Bang, after the beginning of the universe. And at that point, the temperature of the universe would have been this enormous temperature, 100 billion kelvins. It would be glowing, but an enormously high energy light. Okay, at that temperature, some interesting things happen in physics. So the electron has a partner called the positron, has the same mass but opposite charge. And if the temperature is of this range, where the Boltzmann's constant times the temperature is about the energy of the photons that are in the light, that has enough energy to create mc squared to create a positron and electron. So 2 photons can hit each other, annihilate, create a positron and electron, or positron and electron can hit each other, annihilate, and create photons. So that process happens all the time in a plasma at that temperature. And so Gamov's saying, hey, I understand the physics at this level, let's do it. And he could take it all the way back to about that moment in time, about a hundredth of a second after the Big Bang. Okay, so let's start a little stopwatch and see what the universe, at that point he couldn't go back much further because of the laws of physics as understood at the time weren't quite sufficient to go back much further with reliably. But now you can run the clock forward. What's going to happen? Okay, so it's hundredth of a second, the universe would have been light, basically. Let there be light. The first moment of the universe is not so dissimilar than the earliest part of the book of Genesis. It would have been photons, light, electrons, positrons, various kinds of neutrinos, which are subatomic particles that are very light and would be easily created, and then a few protons and neutrons. And this story of a few protons and neutrons is important. So it would have been a whole bunch of these. There would have been a few of these protons and neutrons in about equal numbers. And the reason we know that is we would not be here having this conversation had those not been there at that 100th of a second after the Big Bang. Because those are the things we are made of. We wouldn't exist without them. Okay, interestingly, for every 4 billion positrons, there would have been 4 billion and 1 electrons, plus 1 proton and 1 neutron. That was Gamov's calculation. He showed that that must have been the ratio of the protons and neutrons to the photons and positrons in the universe. So every atom in the universe that we're made of came from this tiny dirt in the earliest moments of the universe. Okay, so starting from that moment in time, we can run it forward again. Run it forward for 1 second. The temperatures drop to about 10 billion kelvins. At that temperature, the temperature is about equal to the mass times c squared of the electron. So they start annihilating. And also, the temperature is less than the energy difference between the neutron and the proton. So suddenly, there'll be more protons than neutrons because the protons are lighter than the neutrons. Again, this is simple application of my field of physics called statistical mechanics. So the fraction of neutrons would have dropped to about 16% at that temperature. But then they stop interacting because there's not enough neutrinos and other particles around to cause them to interact. So they begin to decay, and the half-life of a neutron is about 10 minutes. So when it was 12 seconds old, almost all the positrons have annihilated. All we have are these few protons, the electrons, and a few neutrons, which are continuing to decay. And then there's a moment, about 3 minutes after the beginning, where the temperature has fallen to the point where deuterium, the next simplest nucleus, can form. Deuterium is a proton and neutron. And once that forms, then the universe suddenly can say, ooh, I can gobble up all those neutrons, and those things can quickly get cooked into helium. And the helium is a very stable nucleus, and it's still around with us today. And so his calculation with alpha predicted that the universe should be 75% hydrogen, 25% helium by mass, which is exactly what it is. So he was able to use a theoretical calculation to come up with the recipe for the nuclear structure of the universe. Almost every atom in the universe is one of these two things. The things we're made of, they're like parts in millions compared to the number of those. So they wrote a paper. Whether it's accidentally was published on April the 1st or not, I don't know. But as a joke, he loved the name Alpha, and his name is Gamow. So as a joke, he added his good friend Hans Bethe's name to the paper. So it became known as the Alpha Beta Gamow theory of nucleosynthesis. I think Bethe found out about it when it got published, and he knew he had nothing to do with it. You know? He was a very famous theorist at the time and won a Nobel Prize for some other work later. Okay, so one quick aside, what's the origin of the term Big Bang? The British cosmologist Fred Hoyle thought all this Gamow stuff was a bunch of bunk. And in fact, he went on to a BBC broadcast and said, he didn't say Gamow, he never mentioned Gamow's name in this broadcast, but he says those theories were based on a hypothesis that all the matter in the universe was created in one big bang at a particular time in the remote past. He didn't say it on air, but he told other people, he says, that's ridiculous. Couldn't possibly be the case. He was mortified that that term that he coined on the BBC radio broadcast became the term that almost everyone uses for the beginning of the universe. Okay, so that tells us where the hydrogen helium came from. What about the carbon, oxygen, nitrogen, iron, and all the other heavy elements that we are composed of? And for that, the poet of my generation described that very well. This is Joni Mitchell.
This next song that I'm going to play is about one of these pop festivals that they've been having around the world lately. It's one that I didn't really get to go to. I'd been playing the night before in Chicago with a band, friends of mine, Crosby, Stills, Nash, Young, etc., etc. And it was their first professional appearance, and we were all kind of excited about it. The next night, we were supposed to all play in Woodstock, and I had to do a TV show the next day, so I kind of got left behind because they were having problems getting people in and getting them back out again and everything. So I stayed home in New York, and I watched it on television all day.
But she wrote a song.
By the time we got to Woodstock, we were 500,000 strong, and everywhere there was song and a celebration. And I dreamed I saw the bombers riding shotgun in the sky, and they were turning into butterflies of our nation. We are stardust, billion-year-old carbon. We are golden, caught in the devil's bargain, and we got to get ourselves back to the
That's the poetic description of what where did the carbon come from that we're made of? It was formed in the stars, and the stars exploded into space in supernova, particularly in the earliest portions of the universe, because the stars were much bigger in the very first generation of stars than they are now. They burned up their life very much faster, and they exploded this other material out of the universe. We wouldn't exist without the cooking of the elements inside the stars. So it turns out this was Hoyle's idea, and both he and Gamow were both right in the end. Hydrogen and helium came from the earliest moments of the universe. All the other elements were built inside the stars. Okay, so his collaborators took that one little bit further, that glowing that we talked about from the moment when the atoms were ionized in 300,000 years after the Big Bang. Alpha and Herman was another one of Gamow's students. They calculated that means that stuff that afterglow should still be here, and there should be a 5-degree glow of the universe left over from the Big Bang. They predicted this in 1950, and so this 3,000 degree is going to cool, and it eventually becomes something that's visible. And so we measure this today, and we call it the cosmic microwave background. The universe has stretched by a factor of 1,000 from that moment in time, and so the wavelengths are 1,000 times longer, so they're in the microwave portion of the spectrum, about 10 times the frequency you would use in your microwave oven. And this is experimental data to Planck's curve, and in fact, the most perfect black body in the universe is the cosmic microwave background. Now, there's tiny little temperature fluctuations that are pictured in this picture. There's a few hundred parts per million temperature difference between the hottest and the coolest portions, but it's almost all exactly 2.7 degrees Kelvins. The people that discovered it were Penzias and Wilson. They were electrical engineers. They were not physicists or astronomers. They were working at Bell Labs trying to form a new communication system with satellites. So they had the most sensitive radio receivers available. And they kept noticing this hiss, this in their receiver. And when they calculated the temperature of that, it was 3 degrees Kelvin. And it's like, oh, people began to put that together with people at Princeton, and then they look back, it's like, oh, Gamow and his people predicted this 15 years ago, 13 years ago. So that's the cosmic microwave background. That's the afterglow of the universe, of the beginning of the universe. Okay, so here's the quick version of the universe. So there's this first moment, the Big Bang, and there's this very, very brief moment that was called inflation. And it took 380,000 years for the universe to form this glow. And then the universe became transparent because the atoms were suddenly able to capture all of the electrons. The universe was black, it was dark, and nothing new was creating light for a few 100 million years until the first stars were created. And so this period became the astronomers call this the Dark Ages. First stars were created, they burned out rapidly, blowing these other elements out into the universe, and then the universe kept expanding and has been expanding for this 13.77 billion years. Question? That's a good spot for some questions. Right. So there's the one left over is the one that we're made out of.
How are these electrons generated? Because we know that there's more now because there's more in this room than there was at the beginning of the universe.
No, every element, every electron in this room right now was created at that moment in the past. Okay. It's that one that was left over from the 4 billion.
That generated more?
No, it didn't generate any more. It was just what was left over. Oh. So what we are is this little bit of dirt left over from the beginning. Everything annihilated just turned into photons, the light that heats up the rest of the universe. The one that was left over is what we're made out of. The one electron and the one proton and the neutron, that's what we're made out of. Yes, question?
So that
So this is this is in every single direction in space. That's every single direction in space is shown in that. Like all 4 pi. Surface area of a sphere is 4 pi, as my students been.
How is that image produced?
So what they do is they point a radio receiver at every direction in space and measure the temperature. And some spot, almost all of them are 2.7 degrees. Everything's 2.7 point something degrees Kelvin. Some are a little bit hotter and some are a little bit colder by about a few hundred parts per million. So it's very uniform. So this is actually representing trying to blow up the small deviations in the Earth temperature of the cosmic microwave background. Yes?
So, like, can we see photons that were created before, like, the cosmic microwave?
Every photon that we see from this era is at this temperature. So we can see that with radio receivers. And so it's a microwave receivers are able to receive that.
Why can't we see past that?
Past that, it was this plasma, and you can't see through a plasma. So everything that we would have been, the universe became transparent at that moment when the plasma first formed neutral atoms. They bizarrely call that the point of reionization. It's like what? It was the first time, recombination is the first time these things had ever been combined together in the history of the universe. Yes? Ooh, so the reason it's at 3 degrees Kelvin rather than 3,000 is the redshift. So it's shifted by a factor of 1,000. The wavelength's 1,000 times longer, and that's why it's at 3 degrees rather than 3,000 degrees.
Will it ever get so redshifted that we can't see it?
Well, it'll just keep getting longer and longer wavelengths, and if you have a sensitive enough receiver, you can always receive it. Yeah. Eventually, it'll be in the radio spectrum and then into the long wave radio spectrum, et cetera. So as the universe keeps expanding, this keeps shifting to lower and lower temperature and wavelength, longer and longer wavelength. Back there.
Is the heat map theory based on the point when the cosmic background radiation does reach, like, stop?
It's when the atoms first formed and the universe became transparent. So all of that light could travel for 13 billion years without bumping into anything. The universe is really, really transparent. So most every photon from there has traveled for 13.7 billion years, not having hit anything along the way until we capture it with a radio receiver.
But isn't there a theory that the universe, well, I guess it's that eventually it will expand to the point that there's no more energy to expand with?
That's coming up. So that's the story of what's next, you know. So now we're nearly to the end. Okay, so sounds like we've answered all the key questions, right? Theorists and observational astronomers have put together a comprehensive picture that fits together really well. Whenever anyone look at it a little harder, it seems to work. There are some discrepancies that people are worried about, and that's the way science progresses. But wrong. We're not even close. So here are some of the questions. What happened to those neutrinos I was talking about? They should still be around. Their energy, in fact, their temperature would be about 3 degrees Kelvin, and it's really hard to measure a neutrino that has that low in energy. So those neutrinos we can't measure. But other neutrinos we can. This is a picture actually taken of the neutrinos that come out of the sun, taken at midnight in Japan by letting the detector that's detecting neutrinos only measure neutrinos that are coming up through the Earth. They've traveled all the way through the Earth from the sun. So that's an image of the neutrinos that are coming out of the sun, having traveled all the way through the Earth. So those neutrinos are really interesting things. We have a team here at CU in the physics department that specializes in neutrinos. So we believe they're there. That'd be a Nobel Prize if someone could come up with a good way of measuring those things. What about that part per billion impurity of protons and neutrons? Where'd that come from? The laws of the Standard Model actually allow for a small asymmetry between matter and antimatter. But as best we can tell, the size of that asymmetry is not nearly big enough to produce this 1 part per 4 billion asymmetry. So that's an interesting story in the standard model of the particle physics. Okay, other than that, surely we accounted for everything. What's the answer? No way. This is Vera Rubin. In the late 50s and early 60s, she measured what are known as light curves of galaxies, measuring the velocity of the stars as they orbit the galaxy. And if the galaxy's mass was corresponded to the stars in the galaxy, the curve would look like that. Velocity would go down with distance, but in fact it doesn't. It kind of levels out. And so she proposed that there's something we can't see, and it became known as dark matter. And it turns out there's more dark matter in the universe than there is matter in the universe. There's about 5 times as much dark matter as there is matter. We don't know what it is, but it's there. What about, surely we've covered everything now. No. Dark energy. Dark energy is this Hubble curve here. Look like a straight line. If you really start looking at the data, it's not just, in fact, it should be slowing down, according to Einstein's original theory. It's actually speeding up. So the universe is expanding faster and faster and faster. And to account for that, that outward push is perfectly accounted for by this bizarre thing that Einstein put into the original equation, the cosmological constant. It has all the properties that you need to explain that property. So this dark energy, we don't know what it is, but it's accounted for in Einstein's equation by that parameter lambda. So if we do a pie chart of where the energy in the universe is, this is us. That 4% there is all of the matter in the universe that we would call atoms. There's way more dark matter by energy than there is atoms, and there's way more dark energy than there is dark matter in matter. So the universe is a very peculiar thing. 96% of the universe, we have no idea what it is. So that's fertile ground for scientists to make some progress. Okay, what happened before the 100th of a second? Well, we can actually study that now. This is a picture of a relativistic heavy ion collision where you run 2 heavy ions together at nearly the speed of light. It produces what's known as a quark-gluon plasma, which would have been the material that the universe would have been composed of about 1/1,000,000th of a second after the Big Bang. And so we study this in relativistic heavy ion colliders at CERN and at Brookhaven, and we have teams here in the department that study that. So we're studying the properties of the universe in the first 1,000,000th of a second after the beginning. And there's another weird one. So why is it all the same temperature? The cosmic microwave background is 2.7 degrees in every direction. It couldn't possibly have been in thermal equilibrium across that size of the universe. That's known in astrophysics as the horizon problem. And so the explanation of that is another idea people have created. Much less theoretical or experimental support for it, other than you can't explain things other than doing something like this. The universe, during the very first moments, would have expanded by an enormous factor in this very earliest moments of the creation. And so it's a theory in theoretical physics, and it fixes the horizon problem, the flatness problem, the fact the universe is almost exactly on this knife edge between expanding forever and recollapsing. And it also happened to solve this weird one called the magnetic monopole problem. It's a particle that we should have seen by all accounts in theoretical physics, but no one's ever seen one. So it is something people are still thinking about in some detail. What caused the singularity? Lord knows. People use words like quantum fluctuation, blah, blah, blah. You know, the science there is not as well established because it's in a regime of physics we don't really understand. And what happened before the universe began? Well, we don't know, but the question might not even make any sense, because what we call time may have begun at that moment. So there might not have been a before in the sense of time. Okay, whoop. Okay, what about the future? Well, best we can tell, this expansion, it's not going to just expand and slow down. It's in fact accelerating as it expands. But it's going to eventually get colder and colder and darker and dead. In fact, every single thing that we think of that's interesting in the universe is slowly going to just run out of steam. And so as this exponential expansion might even be followed by what's called the Big Rip, which was mentioned by this young man back here a little earlier. The universe could actually, space and time could be ripped apart by the process of this exponential expansion. Okay, so sorry to end on such a downer, but thank you for your attention. I'll be happy to answer some more questions. And there's 2 more Saturday physics talks this semester. Professor Andrew Hamilton on March 11th will talk about black holes, and Professor Michael Dobson will talk about an interesting legal question that he got involved in a few years ago. You ask a physicist a question, well, we're going to study it, and so he did, and it applies to an airline crash investigation. Questions? Yes, sir.
You touched upon this really early, but is what's causing the universe to expand just that time? It's trying to return to being, I guess, what's the absolute?
Okay, so something, the question is, why is it expanding? And it was like something happened at that singularity at the beginning, and that's all it needed. That was the match that set off the dynamite. And the universe is doing its thing according to the laws of physics as we understand them. Right. Well, we don't know what the match was. That's the key question. What was this fluctuation that caused the universe? We don't know. We know when it happened. We don't know what happened. Yes, sir.
So, I watch a lot of YouTube, but I've seen this one, a theory about pocket reality and a barrier that we cannot cross. So I am assuming that after this presentation, I can take a guess that maybe when the universe is finished expanding, it can likely implode on itself, therefore causing the Big Bang to start again, maybe perform a loop. Is that possible?
So there are one of the ideas is that the universe will eventually stop expanding and eventually recontract and start over again. Maybe that was the source of the last one. We don't know. But best we can tell, the universe lifetime is going to be billions and billions and billions and billions of years longer than the current age of the universe. So if it ever turns around, it'll be way, 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 way in the future. Yes, sir.
Does the expansion of the universe affect either the structure or the dynamics of individual galaxies, or do you have to be on much larger scale?
So the question is, does this expansion affect local things that we can measure, like local gravity and so on? Not currently, but eventually during this exponential phase, that will become a very important factor. And then it will spread space out faster than the stars can keep the planets in orbit, So that's a point far into the future, though. It's a very small effect now at our scale. Yeah. Oh, occasionally. So gravity is still acting. So there are massive groups of galaxies called galaxy clusters, and gravity is fairly effective at pulling them together. So we are being pulled right now toward Andromeda and vice versa. So we are actually going to pass through Andromeda in a few billion years. Now, it's quite unlikely that any single star will hit any other single star in that process, because the galaxies are a very tenuous thing. But the star motion will be completely disrupted by that interaction of the two galaxies. And people study that in astrophysics a lot.
So there's multiple galaxies pulling each other together.
They are, yeah. And we are part of what's known as the Virgo cluster. There's thousands and thousands of galaxies that happen to be close to each other, more closer than average to each other, that form a compact gravitational grouping. Yes?
All the light from the Big Bang is becoming redshifted. Is it becoming blue shifted towards something else?
No, the question is it being blue shifted towards something else? And the best way we understand it is the stretching of the universe is always stretching the wavelengths of the light. So no one is seeing a blue shift. No one in the universe sees anything different than what we see.
As you're right, I did mention the heat wave earlier, but are there other theories for how the universe is
Well, there's lots of theories, and then the question is how much experimental or observational evidence supports any of the theories.
theories that you believe in at all?
Well, the one that seems to